In this video we're going to discuss gravitation, and the first thing to note is Newton's law of gravitation. And that reads that the force of gravity between two masses is equal to the gravitational constant times mass 1 and mass 2 over the distance between them squared. And from this equation we see that mass 1 exerts a force on mass 2, and mass 2 exerts a force on mass 1. And if this force is F, this is minus F. So they're equal and opposite because they're in the opposite direction. And G, the gravitational constant, is equal to 6.67 times 10 to the minus 11 Newton meters squared per kilogram squared. And since force is equal to ma, if we eliminate one of the masses in this equation, we get the acceleration, which is due to gravity, is equal to g times the mass over r squared. Now we have big G and little g. Big G is the gravitational constant, and it is universal and constant everywhere. Little g is the acceleration due to gravity, and that varies based on position and what planet you're on, and it's related to the weight of an object. The other thing to note with gravity, if you have a mass attracting another mass, and this could be a solid sphere or a hollow shell, the gravitational attraction between these bodies acts as if the gravity was concentrated in the center of the mass. So the distance between the two masses, we include the radius of those bodies. I also want to point out the principle of superposition. This states that the net force on an object is the sum of all the individual forces acting on it. So if you have three masses, mass 1, mass 2, and mass 3, they're all exerting forces on each other. The total gravitational force on mass 3 will be the one from mass 2 and the one from mass 1. So all the individual forces will give you a sum that will give you your net force. In the past, we have shown Newton's second law to be equal to F equals mass times acceleration, which could also be mass times g. But the acceleration due to gravity doesn't always equal g. And this is due to three factors. The first factor is that the mass of the Earth is not uniform. It actually can vary depending upon where on the surface you are. The other reason the acceleration due to gravity doesn't always equal g is that Earth is an ellipsoid, not a sphere. It's not a perfect sphere. And the third reason that acceleration due to gravity doesn't always equal to g is that Earth has a rotation. and this affects the actual acceleration of gravity. So the Earth has a centripetal acceleration. A centripetal is equal to omega squared times r. That reduces the observed weight of an object except at the poles where there is no rotation. So if we look at a diagram, here we have the Earth, and looking down on, let's say, the North Pole, but this is not rotating. Okay, so this is the equator. Well, let's say we're weighing something. So here's a spring weight with a mass sitting on it. Okay, now that has a weight given by mg, and the scale is showing a normal force, and this is what we see as weight. So when we look at a weight on a scale, we're actually watching at how hard the scale is pushing up on that weight. So let's say the scale here shows a weight that moves over here. Okay? And again, there's no rotation. Now let's do the same thing. We have the Earth. We're looking down from a pole. But this time we have rotation. So we have an angular velocity of omega. And we have our spring, our scale, our mass. Okay. Now what do we have here? We again have the weight pushing down, mg. We have the normal force pushing up, and that would normally be what we would see as weight. But because of the rotation, we have a centripetal acceleration towards the center. Centripetal acceleration that pulls down on the scale, which reduces what it shows as a normal force. So the centripetal acceleration causes a centripetal force, Fg, that reduces the reading on the scale that shows the weight, which is Fn. And that's why, because of the Earth's rotation, the observed weight is actually less than the actual weight. The actual weight will be correct at the poles where there is no angular velocity. Now let's talk about gravitation inside the Earth. So we're no longer on the surface or above the Earth. We're inside the Earth. So here's the surface of the Earth, and we've come down and we're inside the surface. So this is another sphere, and this sphere is radius r, and the radius of the Earth is capital R, and we have a shell that encircles the area above us. So that's the shell that's above our mass. And the Earth has a mass given as m sub e, and we have a mass of m. So as a body moves into the Earth towards the center, the gravitational forces of the shell above the body cancel out to give a net force of 0. Okay, that means that the forces that are pulling against this mass all end up canceling out to zero. The resulting gravitational force on the body is due to whatever mass is below the body, and it decreases linearly to zero at the exact center. So the actual force is given by force is equal to G times the mass of the Earth times the mass of the body over R cubed times R, where G is a gravitational constant, ME is the mass of the Earth, ME is the mass within the Earth, big R is the radius of the Earth, and R is the radius of the mass from the center of the Earth. And gravity has a potential energy. So let's talk about the gravitational potential energy that we give as U. And if you go through the derivations, we find that the potential energy due to gravity is equal to a minus G times the masses over R. And this shows that as R goes to infinity, potential energy becomes zero. And as R decreases, potential energy becomes more negative, or decreases as well. Let me give you an analogy as to why the potential energy becomes more negative as R decreases. The main reason is that it's due to where we choose our reference point, where U equals zero. With gravity, we choose our reference point at infinity. So this is comparable with, for example, throwing a ball off a roof. So let's say we have a roof, and we're going to throw a ball off the roof, and this is X and Y, and this is at height H. So in this case, our potential energy is equal to mgh. And if we take our reference point to be here, where y would equal 0, then u would equal 0 here as well. And then as y decreases, u becomes more negative as it moves away from our reference point. So when it comes to the planet, here's our planet, and we're a distance from the center of the planet, R. And in this case, R is being chosen as infinity because there u would be equal to 0. And as R decreases, u becomes more negative. So it's the same as throwing a ball off a roof. Depending upon where we choose our reference point of y equals 0 or r equals 0 or infinity, where our potential energy starts out as 0, that will determine what direction the potential energy becomes more negative. Let's also discuss escape speed. So if you fire a rocket or a spaceship off the surface of the Earth, if it doesn't have enough speed, it'll just come down in a parabolic arc and crash to the Earth. So you need to have a certain escape speed or escape velocity so that the rocket can continue basically out to infinity. And if you go through the derivations, you'll see that the escape velocity is equal to the square root of 2g times the mass of the planet over the radius of the planet. And this is for any planet, not just Earth. Now I'd like to discuss Kepler's laws of planetary motion. So Kepler's laws of planetary motion. And there are three of them. The first one is his law of orbits. And this law states that all planets move in an elliptical orbit with the sun at one focus. So if we have an elliptical orbit, we have the sun at one focus of this ellipse, and we have, and if these are the axis of the ellipse, we have a measurement called the semi-major axis, which is the distance from the center of the ellipse to the furthest point past the sun. So A is equal to the semi-major axis. And there's also a measurement from the sun to the center of the ellipse, and it's called E, or sometimes EA, and that's the eccentricity of the orbit. So if we had a circular orbit around the sun, then E, or EA, would be equal to 0. There is no eccentricity or stretching of one axis. So let's look at the second of Kepler's laws of planetary motion. And this he calls the law of areas. And this states that a line that connects a planet to the sun sweeps out equal areas in equal time. So if you have an orbiting planet, okay, if we draw a line and that moves a certain amount of time, dt, to this point, this sweeps out an area here. Let's call that area 1. And now that same planet in that same orbit is now here. And in that same dt, let's say it takes that long to get here, it sweeps out this area 2. And so the law of areas will state that area 1 is equal to area 2. Or dA dt is a constant. And again, the time it takes to sweep out area 1 is time 1, and that's equal to the time it takes to sweep out area 2, or times 2. And this is due to conservation of angular momentum. And now let's look at Kepler's third law, and that's the law of periods. And this says that the square of the period of any planet is proportional to the cube of its semi-major axis. So t is the period, and remember, t is the time it takes to do one orbit, and that's equal to 2 pi r over the velocity. So the third law states that t squared is equal to 4 pi squared over gm times r to the 3. Now this is for a circular orbit. If you had an elliptical orbit, then you would use a instead of r. And so t squared is equal to 4 pi squared times g times the mass times a cubed. And that's for an elliptical orbit. Now let's discuss satellites. So a satellite orbiting around the Earth. So a satellite's speed will determine its kinetic energy, K, and its distance from the center of the Earth, or r, will determine or fix its potential energy, U. So you have a satellite with kinetic energy, potential energy, and those can vary, but its total energy, which is equal to K plus U, remains a constant. So we know that U is equal to minus G M M over R. We can also derive that kinetic energy is equal to G M M over 2R. So the total energy in this case is equal to K plus U, which is equal to G M M over 2R minus G M M over R, which comes out to be a minus G M M over 2R. So that is the total energy in a circular orbit. Okay, if we were looking at an elliptical orbit, then E total would be equal to a minus G M M over 2A, and that's elliptical orbit. Now, let's talk a little bit about Einstein and gravity. And this gets into his theory of relativity, which we'll talk about in a future video. But we can discuss it a little bit here. And one of the things Einstein did, he had a thought experiment, and then he postulated his principle of equivalence. And what he said was that a person feels a gravitational force standing on the Earth the same way he would feel the force of acceleration in an enclosed box in zero gravity space. So what does that mean? If you're standing on the Earth, okay, you have a weight mg. Now let's say you're enclosed in a box or an elevator, and you're standing there, and you're in space, and it's not moving. Well, you'd be floating around in that enclosed box, and you wouldn't feel any gravity. However, if this box starts accelerating up towards your head, you will start feeling the force, the normal force of the bottom or the floor of the box pushing on you. And at a certain speed of ma, that would equal mg. And you would not be able to tell whether you were standing on a planet or moving through space. So that's what he meant by the equivalence. And that's where he came up with the fact that everything is relative. Another thing that Einstein was famous for was postulating that gravity is due to a curvature of space-time, the four dimensions, and this also will cause light to bend. So you can see one of the typical diagrams where the sun is causing a curvature of space-time such that light bends around it, which can change where it looks like the origin of the light is when you look at it. And lastly, we'll talk about black holes. A black hole is an object whose mass is so great that not even light can escape once you are closer than its Schwarzschild radius. The Schwarzschild radius is equal to 2 g times the mass over c squared, where c is the speed of light and m is the mass of the black hole. So basically, a black hole has a Schwarzschild radius, and the gravity is so strong within it, nothing can escape. And in 3 dimensions, this forms a sphere, and that's called the event horizon. Now, yes, Hawking radiation does escape from black holes, but that'll be discussed later on. Let's do some gravitation problems. 2 identical marbles of mass 10 grams are 50 centimeters apart on a flat surface. What is the ratio of the weight of one of the marbles to the gravitational attraction of the other marble? So we know that weight is equal to mg, and force of gravity is equal to g times mm over r squared, which, since the marbles are identical, it's equal to g times m squared over r squared. So the ratio of weight to the force of gravity would be mg over g m squared over r squared, and one of these cancel out, so that becomes g r squared over gm, and then we just put the numbers in. So g is equal to 9.81, r squared is 0.5 meters squared over big G, which is 6.67 times 10 to the minus 11, times the mass, which is 10 grams or 0.01 kilogram. And if you do the math, that comes out to be 3.7 times 10 to the 12th. And that is the weight to the force of gravity. So the weight is 3.7 times 10 to the 12th, greater than the force of gravity between the marbles. Here's another problem. At what point between the Earth and the Moon does the gravitational forces of each cancel out and become zero? So if we have the Earth and the Moon, and gravity acts as if it comes from the center of the mass, okay, we want to know if we're at this point, and let's call this the mass of the person. We'll call the distance to the center of the Earth x1 and the distance of the center of the Earth to the Moon x2. We want to know when is the gravity balanced or equal between the two, such that the force on us is zero. So that means the force of gravity from the Earth has to equal to the force of gravity from the Moon. So let's put these equations in. We get g times the mass of the Earth times the mass of the person over x1 squared equals g times the mass of the Moon times the mass of the person over x2 squared. Those cancel out, those cancel out, and we get mass of the Earth over x1 squared is equal to mass of the Moon over x2 squared, or x1 squared over x2 squared is equal to mass of the Earth over mass of the Moon, or x1 over x2 is equal to the square root of mass of the Earth over mass of the Moon, which is equal to, we have these numbers, 6 times 10 to the 24th over 7.4 times 10 to the 22nd meters, and it's the square root of those. And this becomes the square root of 81, or x1 over x2 is equal to 9. Now, that's two unknowns, so we need a second equation to solve for both of them. Well, we know the distance from the center of the Earth to the center of the Moon, and that's equal to x1 plus x2, and that's equal to 3.8 times 10 to the 8th meters. And if we solve for x1, that's equal to 3.8 times 10 to the 8th minus x2. If we then put that in this equation, we get x1 over x2 is equal to 3.8 times 10 to the 8th minus x2 over x2 equals 9, or 3.8 times 10 to the 8th over x2 minus 1 equals 9. 3.8 times 10 to the 8th over x2 equals 10. And if you solve for x2, you get x2 is equal to 3.8 times 10 to the 7th meters. And then if we put x2 into this equation, we know x1 is equal to x2 times 9. So x1 is equal to 9 times 3.8 times 10 to the 7th, or x1 is equal to 34.2 times 10 to the 7th. So these are the distances from the Moon and the Earth that will give us zero gravity. Here's another problem. What would the period of rotation of the Earth be if its speed increased until an object at the equator became weightless? So let's draw this. Here's the Earth, and we're looking down on the Earth from the pole. So this becomes the equator, and it's rotating with an angular velocity omega. So we have an object at the equator, and we have the weight towards the center of the Earth. We have the normal force pushing up, which is what we consider to be the weight. And we also have a centripetal force due to the Earth's rotation. So let's write our force equation. So we have mg minus normal force is equal to mass times acceleration. Okay, and if we solve for normal force, that's equal to mg minus ma, or mg minus mv squared over r, because that's what the centripetal acceleration is. The other thing that we know is that the period is equal to 2 pi r over velocity, or solving for velocity, that's equal to 2 pi r over t. V squared is equal to 4 pi squared r squared over t squared. And if we substitute that into here, we get the normal force is equal to mg minus m times 4 pi squared r squared over t squared divided by r. So one of those cancel out, and we get normal force is equal to m times m 4 pi squared r over t squared, or m is normal force is equal to g minus 4 pi squared r over t squared. Now, to be weightless at the equator means that the normal force has to equal 0, which is m times g minus 4 pi squared r over t squared. Divide by m, that cancels out, and we end up with g is equal to 4 pi squared r over t squared. And if we solve for t squared, we get t squared is equal to 4 pi squared r over g, or t is equal to the square root of the right side, which is 2 pi times the square root of r over g. And we can put in those numbers. That's 3.14 times the square root of r, which was given as 6.4 times 10 to the 6 meters, the radius of the Earth, over g, which is 9.81. That's equal to 6.28 times the square root of 0.65 times 10 to the 6, or t becomes 5 times 10 to the 3 seconds. And if you divide by the number of seconds in an hour, you get t is equal to 1.4 hours. That's the rotational speed the Earth would have to spin to make an object at the equator weightless. Here's another problem. Estimate the diameter of a spherical asteroid with a density of ρ equals 3 grams per centimeter cubed, from which you throw a ball of mass m that travels to infinity. Assume you throw the ball with a velocity of 30 meters per second. So we're talking about escape velocity of the ball here. So we're given that density is equal to 3 grams per centimeter cubed, which is actually equal to 3 times 10 to the third kilograms per meter cubed. And we know density is mass over volume. So in this case, the mass of the asteroid is equal to density times volume, which is equal to density times 4/3 pi r cubed for a sphere. So we're going to use conservation of energy to solve this problem. So conservation of energy says that our final energy, potential and kinetic, is equal to our initial energy, potential and kinetic. And what we're talking about is throwing the ball to infinity. So r would be equal to infinity. Well, at infinity, the kinetic energy is 0. So our final energies are 0, and the kinetic energy is 1/2 mass times velocity squared plus, in this case, a minus g times the mass of the asteroid times the mass of the ball over r. And this is actually the mass of the ball. So these cancel out, and we get 0 is equal to 1/2 v squared minus g, mass of the asteroid, over r, or 1/2 v squared is equal to g, mass of the asteroid, over r. Or r is equal to 2g times the mass of the asteroid over v squared. Now, we found the mass of the asteroid up here, so this becomes 2g times density times 4/3 pi r cubed over v squared. This becomes 2, and we end up with if you go through this, r squared is equal to 3v squared over 8g density times pi, or r is equal to v times the square root of 3 over 8g density times pi. But we want the diameter, which is twice the density, twice the radius. So diameter is equal to 2r, which is equal to 2 times v times the square root of 3 over 8g density times pi. And we can put these values in. So it's 2 times 30 times the square root of 3 over 8 times 6.67 times 10 to the minus 11 times density, which is 3 times 10 to the third times pi, 3.14, which equals 60 times the square root of 0.6 times 10 to the sixth, which is 60 times 0.77 times 10 to the third, or the diameter is equal to 46.5 times 10 to the third meters, or 46.5 kilometers. One more problem. A satellite is in geosynchronous orbit over the Marco Zero Monument in Brazil, which means it is directly over the equator. At what radius r will the satellite remain fixed to an observer on the ground? So let's diagram this. We have Earth, and we have our satellite above Earth, and the satellite is a distance of r from the center of the Earth. Here's our satellite, and we have the force of gravity on the satellite, and we have the Earth spinning with an angular speed of omega. So we know that our motion equation says that the force of gravity is equal to the mass of the satellite times acceleration. So in this case, this is g times the mass of the Earth times the mass of the satellite over r squared is equal to mass of the satellite times acceleration. These cancel out, and we get g times the mass of the Earth over r squared is equal to, and if you remember, acceleration is angular velocity squared times r, which gives us r cubed is equal to g times the mass of the Earth over angular velocity squared. Now, angular velocity can be calculated by looking at the fact that the Earth does one rotation in 24 hours, which is equal to 2 pi radians over 24 hours, which is 8.64 times 10 to the fourth seconds. So we can use this in this equation, and we get r cubed is equal to g, which is 6.67 times 10 to the minus 11th, times the mass of the Earth, which is 6.0 times 10 to 24th kilograms, divided by omega squared. And if you go through this calculation, this ends up being 7.3 times 10 to the minus fifths radian per second. So we put that in here, 7.3 times 10 to the minus fifth radians per second. So r cubed becomes 0.75 times 10 to the 23rd meters. which is equal to 75 times 10 to the 21st meter. And therefore R would be equal to 4.2 times 10 to the 7th meters.